Okay, hello everyone, and welcome to our lesson on weathering, soil, and mass movements. Now, this lesson we're going to use and review a lot of what we've learned so far about earth science and about minerals. Let's go ahead and get started here. Throughout this lesson, we're going to be talking about this process called weathering. We're here on slide 2. Now we're going to learn about two main types of weathering. But when we talk about, we're going to start with mechanical weathering. This is what occurs when physical forces break rock down into smaller and smaller pieces without changing the rock's mineral composition. Let's look at that. I want to look at a few of those words in there to kind of understand what that means. First, I want to look at that term, break rock into smaller and smaller pieces. What we're talking about here is breaking down. When we talk about breaking down something, that means we break it into smaller or simpler pieces. To give you an idea, here's what's happening. So over here, we're going to start with, we'll call it A. You can see we have something that's large and complex, and that breaks down into things that are smaller and simpler. So things that are large and complex break down into small, simple things. Now, when we talk about things breaking down, this can happen one of two ways. We can have two types of change here. That could be a physical change or a chemical change. Now, we've talked about both of these types of changes in our previous lessons. A few examples of physical change. And I'll go ahead and physical change would be like water freezing into ice, or ice melting, or salt dissolving in water. Examples of chemical changes would be like sugar burning, or photosynthesis in plants, or metabolism in animals and human beings. These are all chemical changes. Remember, our physical change, a change in state of matter, like water freezing, ice melting, a solute dissolving into a solvent, like salt dissolving in water, or sugar dissolving in water. Chemical changes are things like combustion, sugar burning, fuel burning, or photosynthesis in plants. Staying here on slide 2, in nature, 3 physical processes are especially important causes of weathering: frost wedging, unloading, and biological activity. We will talk about all 3 of these one at a time. First, however, I want to look on slide 3. We're looking at this idea of surface area. Now, anytime we have mechanical weathering, anytime we're breaking something down, we're going to increase the surface area. Look at that illustration on slide 3. We see something very similar to this. On the left side, we have a large cube. Now notice the size of that cube is 4. That could be 4 meters or 4 centimeters. We don't have a unit there. but we know that 4 times 4 is 16. So the surface of one face of that cube is 16. We also know there are 6 sides to a cube, which gives us a surface area of 16 times 6 times 1 cube, 96. Now, as that cube breaks down, as it is weathered, as we go through mechanical weathering, that cube breaks down into 8 small cubes. And there we now have 8 small cubes, and each side has a length of 2. So every face has an area of 4 square units. So now 4 square units times the 6 sides of a cube times now not 1 cube but 8 cubes, we now have 192 square units. So you can see by breaking that cube down into smaller pieces, we have more surface area. And the same thing happens when we break each of those 8 small cubes down into 8 even smaller cubes, each with a length of 1 unit, each with a surface area of 1 square unit. A way to think about this that might be intuitive, imagine, so surface area, increasing surface area is going to increase the rate at which physical and chemical change can occur. That's what you need to take away from this. One way to think about this is imagine taking a block of ice. Now, if we left that block of ice out in the sun, eventually it will melt. But it might take, an hour or 2 hours for that ice to melt. However, if we took another block of ice, the same size, the same mass, and we smashed it into small pieces, into tiny little pieces of ice, hundreds of little pieces of ice, that would melt much faster. And the reason is we've increased the surface area. So I want you to think about that example of the large block of ice and the smashed up block of ice. The smashed ice is going to melt much faster. By thinking about that, by imagining that, we can understand how increasing the surface area will increase the rate of physical and chemical changes in rocks. All right, let's move on. Remember, we have our 3 types of mechanical change, which we mentioned earlier in the presentation, that the first type we're talking about is frost wedging. Let's look at those 2 words to figure out what that means. Frost. Notice we have FR, just like the word freeze, because the meaning is very similar. Frost refers to a small amount of water becoming ice. So not if a lake or a river will freeze and become ice. Let's say we just have a surface, instead of a lake or a river, we just have a wet area, like a rock is wet or the grass outside is wet. When that small film of water freezes into ice, we call that frost. So the ice that forms because something is wet, not from a large body of water, but just a wet surface. Wedging. A wedge is something that we use to break something else, something that's driven into something to split it. This would be an example of a wedge. Notice here, if I have a triangle, now this could be maybe an axe. Let's say this is an axe and a piece of wood. When we drive that axe into the wood to split it apart, we refer to that as a wedge. So with frost wedging, we're looking at how frost, that ice, can break rocks apart. Now you might be wondering, how in the world can ice break a rock? Ice breaking a rock makes no sense. A rock is stronger than ice, right? Well, it's important to remember that when water freezes, it forms crystals. So when it freezes, the water molecules are actually farther apart than in liquid water. So in ice, the water molecules are farther apart than in liquid water. So when water freezes, the molecules are farther apart, so the water expands. So if water trickles down into a rock, let's say into a small crack in a rock, and then freezes and expands, it can work like a wedge to push that rock apart. So just as we have our wedge driving down into this piece of wood or whatever it may be, if water trickles down into a rock and then expands, when it freezes, it can actually break that rock apart. You can see a good example of this on slide 5. That rock has been broken apart because water trickled down into that space, maybe a tiny crack in the rock, and then froze and expanded and broke the rock into two pieces. So, frost wedging is our number one method of mechanical weathering. Number 2 is unloading. This is the reduced pressure on igneous rock causes it to expand and allows slabs of outer rock to break off in layers in a process called exfoliation. Remember what we've learned about igneous rock. Remember that igneous rock forms when magma freezes. Remember, magma is that hot liquid rock buried deep in the earth. When that magma cools, it freezes. It goes from liquid rock to a solid rock, from hot liquid rock to cool solid igneous rock. So often that igneous rock is buried underneath layers of sedimentary rock or soil. Now remember what we've learned about sedimentary rock and erosion. Remember, in erosion, water, like in streams and rivers, carries small particles away, and it carries it down into streams, to rivers, and then into lakes and oceans. So if you imagine that igneous rock, when that magma has cooled underground, and then erosion carries away the rock or the soil that's on top of it. You can see a good picture of this on slide 7. Now remember what we learned about sedimentary rock. Remember, it forms because of all the pressure and the weight of the rock and soil on top of it. Well, imagine that igneous rock with all of that weight, all of that pressure on top of it, and then erosion over hundreds of years or thousands of years carries away that soil, carries away that rock on top of the igneous rock. Without that weight, the igneous rock can actually expand because it's under much less weight, under much less pressure. So the igneous rock will actually expand and crack, and that's what we call unloading. And you can see in that igneous rock on slide 7 a lot of different cracks forming as the rock expands. That's called exfoliation. And I have been able to see this in the United States, in the Black Hills. There are whole mountains that look like slide 7, whole mountains of igneous rock, where you can actually see all that slate and shale cracking away. The third type of mechanical weathering is biological activity. This is the activity of organisms like plants, animals, and humans. You can see a good example of biological activity on slide 8. You can see that tree with the roots growing down into the rock. You can just imagine how, as that tree grows, the roots will push that rock apart, just like the wedge that we looked at a few slides ago. Here, instead of water acting like a wedge, it's the root that acts like a wedge, that grows and pushes that rock apart. You can actually see this at a lot of the old temples here in Thailand and down in Cambodia. I remember when I went to see Angkor Wat, there are so many old trees where the roots have grown so thick that they've pushed the rocks aside, they've pushed away the bricks. So yeah, it's very, very impressive to look at, but also a very good example of how biological activity can cause weathering. So those are our 3 main types of mechanical weathering. Frost wedging, from that expansion of the water, the unloading caused by erosion and biological activity from trees, from animals, and from human beings. Next, let's talk about the other type of weathering, chemical weathering. Now remember, we've done a whole unit on chemical reactions. Just to give you one very simple, very easy example, remember this one. We've probably talked about this before. Here we have sodium hydroxide, a base, and hydrochloric acid reacting to form sodium chloride, which is a salt, and water, which is water. So the sodium from sodium hydroxide and the chlorine from hydrochloric acid bond to form salt. They form an ionic bond to form salt. Then the hydroxide and the hydrogen ions bond to form a water molecule. That's an example of a chemical reaction. Now remember what we learned in our lesson about minerals. We learned that a lot of these minerals, like many minerals, are made of many different types of elements, of many different elements. For example, the silicate minerals are always going to contain the elements silicon and oxygen, but they also may contain elements like potassium and other alkali metals. They may contain calcium and other alkali earth metals. They can contain transition metals like iron, cobalt, nickel, and aluminum. All of these elements can take part in chemical reactions, just like the sodium, the hydroxide, the hydrogen, and the chlorine take part in a chemical reaction. So to look at an example there, there on slide 9, the chemical weathering of granite. Remember, granite contains a lot of different minerals. Granite is that really spotty rock that contains many different minerals like quartz and feldspar. There underneath, the weathering of potassium feldspar produces clay minerals, soluble salt like potassium bicarbonate, and silica in solution. The quartz remains unaltered. That means unchanged. To understand why that is, remember what we learned about quartz. Remember, quartz is just silicon and oxygen. It's just a repeating pattern of silicon and oxygen with 2 oxygen atoms for every silicon. So it's very simple. So there are no alkali metals or alkali earth metals or transition metals or halogens that can enter into chemical reactions. So that's why the quartz remains unchanged. The quartz is going to stay the same because it's so simple. It's just silicon and oxygen. However, let's take the other example, the potassium feldspar. Potassium feldspar has potassium, aluminum, 3 molecules of silicon, and 8 molecules of oxygen. So you've got potassium, which is an alkali metal, and aluminum, which is a transition metal. That's a lot more stuff that can enter into chemical reactions. So feldspar is going to change. It's going to go through chemical weathering. But quartz will not go through chemical weathering. More about chemical weathering. The weathering of silicate minerals, like feldspar. This produces insoluble iron oxides and clay minerals. Right. Let's say we have feldspar and we have iron. Let's say we have feldspar lattice and iron nearby. Well, iron will react very readily with oxygen. In the right conditions, if there's water present, iron will react with the oxygen in the atmosphere to form rust. Anytime you see a bicycle or a car rusting, that's the iron reacting with the oxygen. Well, the same thing will happen underground. If there's iron and water and a silicate with a lot of oxygen, like feldspar, we're going to get iron oxide, rust. Spheroidal weathering. This causes the corners and the edges of a rock to be round. We're going to look at a good picture of this spheroidal weathering later in the lesson. Other factors that affect the rate of weathering are the characteristics and the climate. Right, of course. The rock characteristics, the mineral composition and solubility. An example, remember, we learned just like with the quartz and the feldspar, the quartz is not going to react with much, but the feldspar is going to be very reactive, and it's going to form a lot of oxides. Physical features, such as joints. Remember what we saw with frost wedging. If a rock has a crack in it where water can leak in and trickle down, it's going to be more likely to have frost wedging, to form that layer of ice and frost inside the rock that can push it apart. 2, climate. Temperature and moisture are the most critical factors. Let's look at that example of frost wedging. Now, why will frost wedging never happen here in Thailand? You'll never see a rock like that. Back on slide 5. That rock that was split apart by ice. You will never see that kind of weathering in Thailand because it never gets cold enough to freeze here. So climate can play a factor. Chemical weathering is most effective in areas with high temperatures and abundant moisture. Areas like Thailand. So here in Thailand you would not see a lot of frost wedging, that physical change, that mechanical change, but you're going to see more chemical weathering because that's going to happen with a lot of moisture and very high temperatures. On slide 13, you see that picture that I promised you of spheroidal weathering. Yeah, this is the kind of thing you would be more likely to see this in Thailand than in a very cold region, because that warm, moist air is going to cause more spheroidal weathering, more chemical weathering. Moving on, differential weathering caused by variations in composition. This creates unusual and spectacular rock formations. Yeah, sometimes in the same mountain or in the same area you'll have different compositions, different types of rock, and some will weather very quickly and some will weather very slowly. So we get very unusual formations. 5.2. Soil. Soil is a part of the regolith that supports the growth of plants. Regolith is the layer of rock and mineral fragments that covers most of the Earth's land surface. Soil has 4 major components, and we're going to look at this in more detail. Mineral matter. Yeah, soil is all those minerals that we talked about a few lessons ago, which is broken down rock. Humus, which means decayed organisms, other plants and animals. Water and air. On slide 17, you can see that the largest portion of good soil is mineral matter. So good soil is made up of about 45% mineral matter with a good amount of air and water, and then a small amount of that humus, the organic matter. Now, when we look at soil, we describe it by its texture. Texture is the proportions of different particle sizes. Now, sand, we know, has very large particles. Silt is going to be medium particles. Clay, very small particles. Loam, which means a mixture of all three, is best suited for plant life. Let's think about why that is. Why would we want a mixture? Why would we want a lot of different sized particles in our soil? Well, think about it. With sand, we have large particles. So there's going to be a lot of space in between those particles. To give you an example here with an illustration, here, a very quick illustration of sand, you can see that in between the particles there's a lot of space. Well, that space is good for contributing the air. Remember, our good soil is about 25% air. So sand is going to let in air, but it will not hold water. Water is just going to trickle through that sand. So sand So with very sandy soil, we've got air, but we'll have no water. Then let's look at the opposite, clay. Now clay, I've drawn where the particles are so small we can't see them. Now, the water cannot trickle through the clay, so the clay will hold on to the water. However, the air cannot get into the soil. There we go. So our sand lets in air, but it can't hold water. The clay will hold water, but it won't let in air. So with soil that's too sandy, we have plenty of air but no water. With soil that has too much clay, we've got plenty of water but no air. And remember, we need a mixture of both to have good soil. That's why it's good to have a mix of sand, loam, and clay. Or, sorry, of sand, silt, and clay. We can see this in a little bit more detail on slide 39. We've got a triangle where our three corners represent the three basic types of soil: sand, silt, and clay. And then as we move into the center of that triangle, you can see we have a lot of different combinations of soil. And loam is that little area down there at the bottom. And that's what we want to have. So yeah, we're looking at, when we have loam, preferably a soil that's about 20% clay, about 40% sand, and about 50% silt. That would be the ideal mixture. soil particles clump together to give a soil its texture. The most important factors in soil formation are the parent material, the time, the climate, the organisms, and the slope. We're going to talk about all of these one at a time. First, the parent material. The residual soil, that parent material that's in the bedrock. And then transported soil. Remember what we've learned about how minerals and soil and particles are transported by water, by erosion. Transport just means to carry. So remember that the streams and the rivers can carry particles and then deposit them, drop them in other places. That's our transported soil. So the residual soil is like the soil that's been there, the old soil, the transported, the soil that's just moved into the neighborhood. There we go. There's a good illustration of this on slide 22. You can see we see a river valley here with a river flowing through the center of the picture. On the sides, well, we have the slopes of that valley with that thin brown area of residual soil. That's what's developing on the bedrock. We also have the transported soil that's been carried there by the river. This type of river valley we see a lot in parts of the world that have a lot of flooding, or that historically have had a great deal of flooding, where the rivers bring all that soil down, that new soil, what we call alluvial soil. So all that soil that comes down due to erosion is carried and deposited. That's that transported soil, that thin brown line that you can see in the middle of the picture. That's our transported soil. So the residual soil on the sides and the transported soil there in the river valley, in the floodplain. Time obviously is next slide 23. Time obviously is an important factor in all geological processes. The longer a soil has been left to sit and form, the thicker it's going to become. And climate also has a great effect. How much rain, or the amount of rain, is obviously going to affect the amount of erosion. If there's no rain, there's not going to be any erosion. We're not going to have that deposited soil like we saw in the last picture. Another factor would be organisms. Organisms, everything from bacteria to plants, fungi, and animals. All of these organisms are going to influence the soil. They furnish organic material to the soil. That means when animals go to the bathroom, their fecal matter becomes part of the soil. When animals die, their bodies decompose and become part of the soil. So living things are always enriching the soil with organic matter. And that's true of everything from bacteria to plants, fungus, and animals. And then finally, the last factor, slope, angle. Steep slopes often have poorly developed soils. I think if you remember what we've learned about erosion, this is easy to understand. If you have a steep slope, erosion is going to carry all of the soil away. So there's not going to be any soil left there. However, if there's a flat, undulating upland surface, erosion can't carry away the soil. So remember the picture we looked at on slide 22, all of that transported soil. Well, that transported soil is all soil that eroded from farther up the river, from somewhere farther up into the mountains. Well, if you went to that area, you would find that the soil is very poor because the soil keeps being washed away. All of the organic matter keeps being washed away, carried away, and deposited in the river valley. Slide 26. Soil varies in composition, texture, structure, and color. Soil horizons are zones or layers. A soil profile is a vertical section. To break that down a little bit further, we look at three different horizons. The A horizon, which is known as topsoil. You can see all of this on slide 27. So checking out slide 27, we see at the top the A horizon, the topsoil. The B horizon, subsoil. You're going to find a lot more clay and a lot of other particles that have been washed down from the A horizon. And then the C, which is between B and all the unaltered parent material. So the topsoil is going to be where you have the decayed organic matter, the mineral matter. That's going to be the richest soil. That B level, the gray area, you're going to have a lot of clay. And then C, there's going to be partly weathered parent material, like the bedrock that's becoming weathered, that's becoming broken apart. Remember what we learned about weathering, how all those different processes that can break down that rock. You can see down at the bottom that parent material, the bedrock, that gray rock at the bottom, is being broken down. And you can see a good real-life example of this on slide 28. In this picture, they've dug a path through the side of a hill to build a road. And so you can see the straight wall there of the earth, and you can see the different layers. You can see that the topsoil, and then that heavy bedrock at the bottom, and then the area where that rock is being broken up, it's being broken down to become part of the soil. There are three main types of soil that we're going to look at: pedalfer, pedicel, and laterite. Pedalfer. This is what we find under forests, in forest vegetation. They have a lot of those iron oxides and the aluminum-rich clays in the B horizon. Remember what we learned, for example, feldspar. Again, remember feldspar has aluminum, as do many other minerals. So those those minerals like feldspar are going to help create clay. Remember, that's the very small particles. Clay with a lot of aluminum. And we're going to find that in the B horizon. But we see a lot of that in the thing to remember about pedalfer soils. We find them under forests. The next type, pedicel, that's where we get that it's an accumulation of calcium carbonate. Remember from our unit on minerals that calcium carbonate, which is CaCO3, our calcium carbonate, this is what we find in minerals like limestone, as well as chalk and metamorphic rock like marble. So areas that are rich in limestone and marble, that's probably where you're going to find your pedicle soils. Areas that have a lot of feldspar, that's where, and silicates, that's where you're going to find your pedelfer soils. So you can see there's a relationship here between the types of minerals that develop in an area and the types of soils that develop from those minerals. Pedicle soils are associated with dry grasslands. Then the third type, your laterite soils, that's where you get the intense chemical weathering from hot, wet, tropical climate. A lot of weathering. Finally, erosion. We know we've already talked about erosion several times. We talked about this with regard to minerals. We talked about it with regard to rocks. We know that water erodes soil. Water carries those small particles, transports them, deposits them in other places. Human activities that remove natural vegetation have greatly accelerated erosion. Remember, we talked about this in our lesson on pollution. When we talked about water pollution, how plants, vegetation, their roots hold the soil almost like fingers. So when we remove those plants, it's like taking out the hands, and there's nothing to hold the soil, so it washes away. Reservoirs can fill with sediment. They can be contaminated by pesticides and fertilizers. There are many different ways to control erosion. We can plant rows of trees called windbreaks to stop the wind from eroding soil. We can terrace hillsides. Let's say we have a hillside like this. We're worried about, if we're worried about erosion, one thing we can do is build terraces. That's flat areas like this. So now the soil cannot be carried away. We've created like a stairway down the side of the mountain. I saw a beautiful example of this when I went to Bali. You can see in Bali they've made rice fields on the sides of all of the mountains by building these terraces one at a time around the mountains. So now going down the mountain you have these steps, these flat rice fields. So they control erosion. Plowing along the contours of the hills, yes, very similar concept. Instead of plowing straight up and down, contour farming, very important. And rotating crops, making sure you don't plant the same crop in the same place year after year after year, because that will be bad for the soil. Mass movement. This is, you can think about erosion, how erosion, with erosion, the water carries the particles, but it carries particles of rock and soil very, very slowly, in a very slow fashion. With a mass movement, a large amount of rock or soil moves all at once. This is the transfer of rock and soil downslope due to gravity. Among the factors that trigger this mass movement: saturation of surface materials with water, oversteeping, the removal of vegetation, and earthquakes. Remember, removal of vegetation, just like that, causes erosion, and we saw that especially in the unit on pollution, where we looked at that mine. Also, it doesn't have to happen slowly. It can happen very, very quickly, and that's a mass movement. And then finally, earthquakes. There's a good picture of a mass movement on slide 36. We can see a huge amount of land, of soil and rock, and even some of the trees have moved down that hill, kind of collapsed all at once. This particular mass movement is what's called a slump, and it was caused by heavy rains. Let's go back to slide 35. We can see two main types of mass movement: a slide or a slump, that downward movement that it looks like it just collapsed. It looks like something was pulled out from underneath. That's a slump. In a slide, all that material comes rushing down the side of the mountain. Another type would be a flow. Flows are mass movements containing a large amount of water, like a mud flow or an earth flow. And then finally, a creep. Now, creep is is much slower, and it's a little bit more difficult to understand. There's an illustration there on the last slide, slide 39. Remember what we learned about water and how when water freezes, it forms crystals. So the molecules are actually farther apart. So when water freezes, it expands. Now, creeps occur when, over the years, the expansion from freezing pushes the particles out, and then when they settle, they come straight down. So each arrow there might represent 1 year, with that land freezing and expanding in the winter and then thawing in the summer, in the spring. So over years and years, that land, those particles are pushed out and down, out and down, out and down, and slowly they make their way down the mountain. That's what's called a creep. Obviously, there's just one particle in this picture. Try to imagine that same thing happening with all of the particles that make up that mountain. So imagine that process 100,000 times over, and that's a creep. So that's it. That finishes our lesson on weathering, soil, and mass movements. What I'd really like you to take from this is an understanding that soil is a very important resource, and good soil is a very precious resource, because it is very difficult to get that right combination of sand, silt, and clay and organic material that is good to use for farming. And there are a lot of different threats to that resource, a lot of different ways for us to lose that soil. So it is very important for us to take whatever measures we can in order to conserve and preserve that soil resources. All right. Thanks very much for tuning in, and I will see you next time. Thank you. Okie dokie.